Welcome all of you in this session. My name is Dr. Vishal Patil. I am working as an associate professor in Department of Mechanical Engineering. In today's session, we will study the fundamental things related with the energy. Content for this online session is first one is forms of energy, second one is internal energy, third one is nuclear energy, and fourth one is mechanical energy. First important point is forms of energy. The energy can exist in the forms of just like thermal energy, mechanical energy, kinetic energy, potential energy, electrical energy, magnetic energy, chemical energy, nuclear energy, and their sum is known as total energy of the system. It is denoted by capital E. The total energy of the system on the unit mass basis is denoted by small e is nothing but capital E divided by m in kilojoule per kg. Thermodynamics provide no information about the absolute value of the total energy. It deals with only change of total energy, which is what matter in the engineering problem. Thus, the total energy of the system can be assigned a value of 0, means capital E is equal to 0 at some convenient reference point. The change in total energy of system is independent of reference point selected. In thermodynamics analysis, the various forms of energy that make up the total energy of system in two groups. First one is macroscopic and second one is microscopic. The macroscopic form of energy are those of system processes as whole with respect to some outside reference frame, such as kinetic and potential energies. The macroscopic form of energy are those related with the molecular structure of system and the degree of molecular activities, and they are independent of outside reference frames. The sum of all the microscopic form of energy is called as internal energy of the system, and it is denoted by capital U. The term energy was discovered in 1807 by Thomson Young, and its use of thermodynamics was proposed in 1852 by Lord Kelvin. The term internal energy and its symbol capital U is first appeared in the work of Rudolf Clausius and William Rankine in the second half of 19th century, and it is eventually replaced the alternative term inner work, internal work, and intensive energy commonly used at the time. The macroscopic energy of system is related to motion and the influence of some external effects such as gravity, magnetism, electricity, and surface tension. The energy that a system processes as a result of motion relative to some reference frame is called as kinetic energy. When all parts of system move with the some velocity, then the kinetic energy is expressed in the form of Ke is equals to 1 by 2 mv square in kilojoule. The kinetic energy of rotating solid body is given by 1 by 2 I w square, where I is the moment of inertia of body and small w is the angular velocity. The energy that system processes as a result of elevation in a gravitational field is called potential energy. It is denoted by capital PE, and it is expressed by PE is equals to, means potential energy is equals to mgh. In magnetic electrical surface tension effects are significant in some specialized cases only and are usually ignored. In the absence of such effects, the total energy of the system consists of kinetic energy, potential energy, and internal energies, which is expressed as capital E is equals to capital U plus KE plus PE, means total energy is equals to internal energy plus kinetic energy plus potential energy. Means capital E is equals to capital U plus 1 by 2 mv square plus mgh in kilojoule. The most closed system remains stationary during the process and thus they experience no change in their kinetic and potential energies. The closed systems whose velocity and elevation of the center of gravity remains constant during a process are frequently referred to the stationary system. The change in total energy means delta E of stationary system is identical to change in its internal energy means delta E capital U. In this text, the closed system is assumed to be stationary unless the stated otherwise. The next important point is internal energy. The internal energy is defined as the sum of all the microscopic forms of energy of the system. It is it is related with the molecular structure and degree of molecular activities and can be viewed as a sum of kinetic and potential energy of the molecule. To have a better understanding of internal energy, let us examine a system at the molecular level. The molecules of a gas move through the space with some velocity and thus the possesses some kinetic energy. This is known as translation energy. The atoms of polyatomic molecule rotate about an axis and the energy associated with this rotational is rotational kinetic energy. The atom of polyatomic molecule may also vibrate about their common center of mass and the energy associated with the back and forth motion is vibration kinetic energy. For gases, the kinetic energy mostly due to translational and rotational motion, with vibrational motion becoming significant at high temperature. The electrons in the atom rotate about the nucleus and thus possesses the rotational kinetic energy. The electrons at about the outer orbits have larger kinetic energy. The electrons also spin about their axis and the energy associated with the motion is the spin energy. The other particles in the nucleus of the atom also possesses spin energy. The portion of the internal energy of the system associated with the kinetic energies of the molecule is called as sensible energy. The average velocity of the degree of activity of the molecules are proportional to the temperature of gas. Therefore, the high temperatures and molecule possesses higher kinetic energy and the result of this system as a higher internal energy. The internal energy is also associated with the various binding forces between the molecules of substance, between atoms within the molecule, and between the particles within an atom and nucleus. The forces that bind the molecules to each other are, as the one would accept, the strongest in the solids and weakest in the gas. If sufficient energy is added to the molecule of solid or liquid, the molecules overcome their molecular force and break away, turning the substance into gas. This is phase change process. Because of this added energy, the system in the gas phase is at the higher internal energy level than it's in its solid or in liquid phase. The internal energy associated with the phase of the system is called latent heat. The phase change process can occur without the change in chemical composition of the system. The most practical problems fall into the category and one does not need to pay any attention of the forces binding the atoms in the molecule to each other. An atom consists of neutrons and positively charged photons bound together by very strong nucleus force in the nucleus and the negatively charged electron orbiting around it. The internal energy associated with the atomic bond in the molecule is called chemical energy. During a chemical reaction such as combustion process, some chemical bonds are destroyed while others are formed. As a result of the internal energy changes, the nuclear forces are much higher than the forces that bind the electrons to the nucleus. The amount of energy associated with the strong bond within the nucleus of atom is itself called nuclear energy, which is shown in figure. We need not to concern with the nuclear energy in thermodynamics unless, of course, we deals with the fusion and fission reaction. The chemical reaction involves change in structure of electron of atoms, but at a nuclear reaction involves change in the core or nucleus. Therefore, the atom in its identify during the chemical reaction, but loses it during the nuclear reaction. The atoms may also possess the electrical and magnetical dipole moment energies when the subjected to external electrical and magnetic fields due to the twisting of magnetic dipole produced by the small electrical current associated with the orbiting electrons. The forms of energy already discussed, which is considered of total energy of system, can be contained or stored in a system and thus can be viewed as a static form of energy. The forms of energy not stored in the system can be viewed as a dynamic form of energy or the energy interaction. The dynamic form of energy are recognized at the system boundary as they crosses it, and they represent the energy gained or lost by the system during the process. The only two forms of energy interaction associated with the closed systems are heat transfer and work transfer. An energy interaction is heat transfer if its driving force is temperature difference. Otherwise, it is work transfer, as explained in previous lectures. A control volume can also exchange of energy via mass transfer since any time mass is transferred into or out of the system. The energy content of the mass is also transferred with it. In daily life, we frequently reference the sensible and latent forms of internal energy as heat, which heat is nothing but energy transfer without change in mass. We talk about the heat content of bodies. In thermodynamics, however, we usually reference the forms of energy as a internal energy to prevent of any confusion with the heat transfer. The next important point is nuclear energy. The, it is related with the fission reaction involves the split of uranium atom means uranium 235 isotope into other elements and it is commonly used to generate electricity in a nuclear power plant and it is also used in power nuclear submarines, aircraft carriers, power spacecrafts and building a nuclear bomb. The percentage of electricity produced by the nuclear power is 78% in France, 25% in Japan, 28% in Germany, 20% in United States. The first nuclear chain reaction was achieved by Enrico Fermi in 1942. The first large-scale and nuclear reactor were built in 1944 for the purpose of producing the materials of uranium weapons. When uranium-235 atom absorbs a neutron and split during the fission process, it produces a cesium-140 atom and rubidium-93 atom, 3 neutrons, and 3.2 into 10 raised to 11 joule of energy. In practical terms, the complete fission of 1 kg uranium-235 release 6.73 into 10 raised to 10 kilojoule of heat, which is more than the heat released when the 3000 ton of coal are burned. Therefore, for the same amount of fuel, a nuclear fission reaction releases several million times of more energy than chemical energy. The nuclear energy by fusion is released when two small nuclei combine into a larger one. The huge amount of energy radiated by sun and other stars originated from this same fusion process that involves the combination of two hydrogen atoms into helium atoms. When two heavy hydrogen means deuterium nuclei combine during fusion process, they produces helium-3 atom of free neutron and 5.1 into 10 raised to 13 joule of energy as shown in this figure. The fusion reaction are much more difficult to achieve in practical because the strong repulsion between the positive charged nuclei called Coulomb repulsion. To overcome this repulsive force and enable two nuclei to fuse together, the energy level of the nuclei must be raised here, heating them about 100 million degrees Celsius. But such a high temperature found only in stars or exploding atomic bombs means A bomb. In fact, the uncontrolled fusion reaction in the hydrogen bomb in nothing but H bomb is initiated by a small atomic bomb. The uncontrolled fusion reaction was achieved in early 1950s, but all the efforts since then achieve controlled fusion by massive layers, powerful magnetic fields, and electrical currents to generate the power have failed. The next important point is mechanical energy. In many engineering systems are designed to transport a fluid from one location to another at specified flow rate, velocity and elevation difference, and the system may generate mechanical work in turbine or may consume mechanical work in pump or fan during this process. They do not involve any heat transfer in any significant amount and they operate essentially at constant temperature. Such systems can be analyzed conveniently by considering the mechanical forms of energy only and the frictional effect that causes the mechanical energy to lost means that is to convert it the thermal energy that usually cannot be used as any useful purpose. The mechanical energy can be defined as the form of energy that can be converted into mechanical work completely and directly by identical mechanical devices such as ideal turbine. The kinetic and potential energies are familiar forms of mechanical energy. The thermal energy is not mechanical energy. However, since it cannot be converted to work directly and completely according to second law of thermodynamics, the pump transfer mechanical energy to the fluid by raising the pressure and the turbines extract the mechanical energy from the fluid by dropping the pressure. In this online session, we have studied the basic fundamental things related with the energy, which consist of total energy, internal energy, mechanical energy, and nuclear energy. For more details, you can refer the reference book Thermodynamics, written by Eunice Frangel and Michael Boles. It is a Micro Hill publication book. It is a 8th edition in SI units. We will discuss next concepts related with the thermodynamics in upcoming video lectures. This video is specially prepared for the teaching purpose of UG students for the understanding the fundamental concepts related with the thermodynamics. One multiple choice question means MCQ question uh, paper is available in the description of this YouTube. Uh, you can solve this question. For this question, you can refer whole video. Thank you very much for the patient listening.